Okay. So, uh, obviously this is still a work in progress. Just going to give you a rundown of what I have so far. Basically my idea to make the algorithm a little simpler. I guess I'll go over what the problem was. So basically we are trying to solve the sum of all square submatrices in a larger matrix, and given a value v, check all those sums and see if there's a match. And if there's a match, we're going to break. So the original algorithm that we were given was a brute force solution, went through every single one. There's a lot of overlap. So first thing I noticed was that a lot of redundant calculations were being done. So my idea to simplify the brute force solution was to create another matrix and basically pre-process the original matrix and create a new matrix of all the sums. So the biggest change that I implemented here was the line 69 here. So basically what we do here is we take in the matrix and we take in the length and the width of that matrix here. Create a new matrix called summation matrix. Set the upper left-hand corner to be the same. Pre-process the first row, pre-process the first column, and then pre-process the rest of the matrix. So time complexity here is big O of n squared. And as you'll see, it returns the summation matrix. And then when check matrix is called, we don't have to do all those redundant checks. When check matrix is called, we run the pre-process summation matrix, set that to be the pre-process here. This is just the length and the width of the matrix. Sorry if I'm not being clear. I'm sick right now. Minimum value. So this is just so that we can go through squares. We don't want to have it. So basically the summation matrix is going to have every possible value, and that includes 1x2s and other rectangular matrices, but we're only interested in squares. So the following code block is really just handling the squares. So this is where the time complexity is highest. It's big O of, I have it written down here, big O of y cubed, because in this particular scenario, y is larger than x, so it's big O of y cubed times x. If x were larger in a rectangular case, then it would be big O of x cubed times y. So that's worst case, and then best case would be big O of the size of the matrix, because you have to run it through the pre-process, and then when you call check matrix, if it's the first one in that upper left-hand corner, then you'll break. You only have to go through the loops one time. So that's the gist of what we're doing here. Checking all the different squares and then breaking when the value v is found. And we're doing that by pre-processing the original matrix so that we don't have to calculate those redundant solutions that have already been calculated. So I haven't made it super far in the proving a lot of this stuff. I've been working with other people. I understand the gist of it, but obviously when I move forward with the workshop video, I'll have all of this more clear. But the loop invariant, obviously we're going to break when one of the submatrices is equal to V. We're going to pull up my code again. So first thing we're doing is we're checking the upper left-hand corner. And then we check the first thing we do is we process the upper left, then the first row, then the first column, then the rest of the matrix, and then we move into check matrix, and our loop ends up breaking if the total of that sum equals to V. So that's our break condition. We end up checking the entire matrix for sure because we're starting with the upper left-hand corner. Then we process the first row. My matrix 0. J is equal to 1 because we already did 0, 0. So J is our row, I is our column. And then for the rest of the matrix, we just go ahead and subtract those J values. Sorry. Do that here. Because those have they've already been calculated. So this is one of the parts that I struggled with a little bit, but I get the gist of it. Pull up an Excel spreadsheet, but basically you're getting you have a submatrix that's progressively getting larger, and you're just subtracting off the rows and the columns, top and the left or top and the right, from that square. So that's basically how that works. So the loop condition is if the submatrix is equal to V, and we definitely process the entire matrix. But that's obviously a part that I need to approve more thoroughly. Let me double check to see what else we got here. I also need to go over space complexity. I remember that. Okay, so big O worst case, big O best case, space complexity. I'm gonna end up having to do that still, and I'll get that done by Tuesday. Proof of correctness. So I've got part of the loop invariant done. I still need to go over the different conditions. That's it. It's about where I'm at right now. Obviously still got a lot of work to do. But I look forward to your feedback. Thank you.